Welcome everybody to Friday. So today, today we're going to be talking about linked lists, and linked lists are one of the hardest topics in computer science for people, and it's one of the challenges because they involve pointers, and people always have trouble with pointers. Linked lists and binary search trees both involve pointers, and those are both considered like the hardest topic in data structures to learn. So what we're going to do today is sort of a soft pitch, a little underhand throw to you guys to get you guys going. We're going to write a little bit of linked list code by hand so you can kind of get an understanding of how the pointers work and how the arrow operator works and this kind of stuff. We've talked about it before, but we're going to be sort of building it a little bit by hand. And then later on in the class, we're going to build an actual linked list class the proper way using proper class design. Your homework assignment, Bridges Shakespeare, is half histogramming, which we did on Wednesday last class, and it's half linked lists, but the amount of linked list code you have to write is minimal. It even tells you which kinds of lines of code you have to write. It's really designed to be sort of a gentle on-ramp to linked lists so that for your next homework assignment, you're going to be able to be a little bit more comfortable and confident with these kinds of things. And eventually you'll begin thinking with with pointers. And you'll be able to, why does it feel like I've said this all before? Weird. What, this is one of the hardest topics? No, the only thing that I've ever said that on for is pointers, really, in this class. I don't think I'll say like something's an important topic, like hash tables are an important topic. I don't think hash tables are really I don't think they're that hard to understand. It's always the pointer stuff that gives students the most trouble. And so I said a couple weeks ago, this is one of the hardest topics because we're doing pointers, and now we're using pointers. And when I introduced pointers, I said, you're not going to have any, like, it's not going to make sense to you why people would use it until today. So today we are going to be using pointers. Yay. And that's why I like the pointer topic. Oh, you're being dramatic. Okay, fine. The pointer topic in Zybooks introduces linked lists because really nobody writes code like integer pointer x equals new integer 5. Like, people don't do this. They just don't. Like, they just make integer x and they set it equal to 5. Like, come on, let's be real here. Okay. So what is a linked list? A linked list at its simplest level, you can make a very simple linked list like this. Integer x, node pointer next, and there. That is a linked list. Okay. That is it doesn't look like much, right? It's just, it's a linked list of integers. So if you want to hold integers like using vectors, you could say like a vector of integers named vec is equal to 5, 10, 15. If we want to hold this in a list, well, I'll show you how we can hold 5, 10, and 15 in a list. Those are the data values we're going to be holding. So every linked list contains two things if you're designing it like this. Every linked list contains two things. One, a single integer, and two, a pointer to another linked list. Okay? And if there are no linked lists following me, then we set the pointer equal to null. Now, I set it to 0 for a reason here. Normally, when you do this in C++, you're going to type null pointer. That is the Bjarne's TrueStrip approved method of setting something to null. But I'm going to set it to 0, which is the C way of doing things. Also in C, you'll see people type this. Null is literally just the number 0. I'm going to do it like this for a reason, okay? And it is setting the pointer to be a null pointer. What happened here? I heard a beep. I don't know. Okay, I'm setting it to be a null pointer, and that means that there are no lists following me. So if there's nobody after me in the list, it's got a null pointer following. Okay, so let's do this by hand. So let's make a node pointer called first that is equal to new node with a value of 5, and I could pass in here null pointer as the next, but I don't need to because it is going to initialize the next pointer to be null. So we got first, we got second, and we got third. CW second, CW, what's going on here? CW third, and let's line these equal signs up, and we're going to have 5 and 10 and 15. So what we have here is not quite a linked list yet because they're not linked together. if I were to ask you, what is his next value set to? What value is this? Everybody, what is the next pointer set to on the first pointer? I'll pause the stream. Answers on chat. Okay. I've also opened my door because the heater is on right now and it's driving me crazy. Okay. So yeah. So first next is set to null because that's what it initializes to by default. We print it out, we're going to get 0. Okay. So a null pointer is really just the number 0. Memory address 0. Now, if we ever try to like use that, if we ever try to dereference that pointer, for example, if we try doing this, what value does the linked list have at memory address 0? Then, anyone want to know what happens when you dereference a null pointer? If you ever have a null pointer, which is this is null, and you dereference it by using the arrow operator off of it, do you guys know what happens? 0 zone, the minefield of doom, right? So Bret Hart, the greatest that is, that was, and ever will be.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer. Open your eyes.
That's what happens, okay? So you run it, boom, segfault, core dumped. A student in the 12 o'clock section said, what is core? And so back in the 70s, we had these things called core memory, which was actually woven by hand, like silk threads and like magnets and things like that. We don't have core memory anymore, but we still say dumping core, which means you're writing the contents of memory to disk. And that would normally create a file called a core file. But I actually have core dumping disabled on the server because my hard drive was constantly filling up with core files because it dumps memory to disk. And then students wouldn't delete them, and so the hard drive would fill up. And so I actually have core dumping disabled. It's actually really useful. Like when I do development on my own, I make sure to turn on core dumping. Because you can do like gdb a.out core, and then it'll actually load your program with the core file. The core file is like a post-mortem. Like at the moment of death, this is what's in memory. And it'll actually say, oh, you crashed on line 53. Then you do things like print the value of X and print the value of this and print the value of that and see what the state of the program was at the moment of death. It's really useful. But you guys kept filling up my hard drive, so it's off right now. So it is an autopsy. Yeah, exactly. So yeah, don't ever dereference a null pointer. If you ever have a null pointer, don't ever do an arrow off of it. Now you can use it, like you can even do something like this. You could say second points to next equals first points to next. So we're copying the value, because remember, this value is just the integer 0, right? So we're just copying 0 from here into here. That's fine. This does not cause a seg fault. It's when you use the arrow operator on a null pointer that you're going to die. Okay? If you do that, then it's going to seg fault, right? Boop. Oh. Seg fault. There. The optimizer got rid of the seg fault for me. Okay, so you can copy the value over, but if you ever dereference a null pointer, then you seg fault. Okay. So how do we link these things up? We do something like this. We say first next is equal to second, and seconds next equals third. Now you don't write code like this in like actual production code. You have functions. I'm going to show you guys later on how to do this. But this is just kind of like, I'm just kind of showing you the manual way of like building a linked list. So let me switch over into OneNote and draw this for you. So new page. We are on 2.10.23. Linked list time. Boom. All right. So what we have here with our code is every linked list. Let's see if I can line this up right. Every linked list has two member variables. It's got an X and it's got a next. Okay. And so we got an X, we got a next. And so if we've got a pointer called first, and first is pointing at this location here, And then we've got another guy, and he's got a value of 5, and by default, it is initialized to 0. Make it a little smaller. And then we got second. And second is pointing at this chunk of memory where it's got a value of 10, or 16 if I can't write properly. 10. And its next is initialized to null. And I've got a third guy whose value is 15 and whose value is null. This is what we got at the beginning. So after these 3 lines of code here run, new node, new node, new node, each of them have a next of null. This is a unlinked list. This is not a linked list. They're not linked together at all. And so with a linked list, normally what you have is one element pointing to the next element, and that guy's next pointing to the next element. And that's what we've done here. So first points to next equals second. So second is pointing at this chunk of RAM. If you were to print out second to the screen, it would be like 0x7FFF53421 or something like that. We're copying the value of this pointer into this pointer here. And so the way that we draw this is like this. Like that. And then when we say seconds next equals third, we're copying the memory address held in third into that pointer there. And too much. There we go. Too much. Ah. Oh, the button. There's a button on this clicker thing here. Nope. It's just doing its thing. How about now? Nope. Nope. This is really frustrating. Okay. Nope. Nope. There we go. There we go. Okay, cool. It just starts going crazy. All right. And then second points to next equals third. And the third's next, we're going to leave it null. Because what null means is there's nothing further. We're at the end. Okay? End of list is null. Okay. So how can we insert something into this list? Like, let's say we want to put something in between 10 and 15. This is what linked lists are good at, by the way. So linked lists are good, like, the only reason to ever use them, really, at inserting in the middle. That's really it. They have order 1 inserts when you have a pointer at something. A vector, when you insert in the middle of a vector, it's got to move. Like if you have a vector of size 1 billion and you insert in the middle, it's got to move, in elements to the right. Worst case, it moves all billion to the right 1 spot and then puts the 1 in. With a linked list, you can actually do pointer tricks like this, like I'm about to show you. And you can put something in between 10 and 15. So if I wanted to put the number 42 in between 10 and 15, I could do this. Second points to next equals new node 42 and second points to next. Now this might hurt your brain a little bit. So let's go over what's happening here. So let's say that delete to caret. Let's say we're just doing this first, okay? Because the new takes place before the assignment. Why is it called a node? Because every individual bit of a linked list is called a node. It comes about from one of the greatest computer science movies of all time called Pitch Perfect, where one of the singers in the show gets nodes in her throat. So in honor of the horrible tragedy of that singer getting nodes, we now call all points in a linked list a node in honor of that. So Pitch Perfect. I think I'm murdering some of my students. Okay. Alessandra, have you seen Pitch Perfect before? Yes, well, all 3 are just the first one or the first 2 parts of it. Yeah. I've watched the first movie like 3 times. I'm I'm not ashamed to admit it. It's actually a very, very funny movie. I've seen parts of Pitch Perfect 2. I heard Pitch Perfect 3, though, was pretty bad, so I didn't watch it. Okay. So anyhow, where was I? Nodes. Yes, these are nodes. Each individual element of the linked list is just called a node. That's the vocab. Okay. So we want to insert something here. Okay. So the first thing we do is the new. And so we're going to new a new chunk of memory that contains an X and a next. And its value is 42. And his next is set to be second points to next. This is second points to next. It's pointing at third. I could have typed third here, but I wanted to do this to kind of make a point. So we're newing this memory first, and it looks like this. And now if we just stopped there, if all we did was delete 3 words, if all we did was this, then we're in bad shape, right? Because we haven't linked this guy's still going to be pointing at third, so we're going to have like a memory leak going on here, right? We're going to lose that memory. So what we do is, one more, there we go, is second points to next equals new node. So this is going to set seconds next, boop, to be you. And so now you can see here, we did not need to do 1 billion operations to insert something in the middle of the linked list. Even if we had a billion nodes, we were able to just go boop and just with one operation kind of insert it into the middle because we got pointers. And so every time we want to make a new thing, we could just use pointer tricks and just put things in. If we want to delete things out, we can just do this, boop, and then that thing in the middle is deleted. Too much deleting. So yeah, we can insert and delete in the middle of a linked list without having to shift a billion things. And so at inserting and removing in the middle. Order 1 inserts. And deletes when you have a pointer at something. Okay. So we can do it again. So if I wanted to insert something before the 42 here, it's like resizing a chain for jewelry. Yeah, it's exactly right. Like, for example, linked lists are often named LLs because LL Cool J would have a cool amulet with different links on it. And you kind of string them together. Yep. So nobody's biting on that one. Okay. So if we wanted to add a new node, okay, in between 10 and 42, like we wanted to do something like this. Amazing computer science history. I know. I only teach the absolute truth in this class. So if I wanted to make a new node here and put in 16 and link it up like this, how would I do it in code? How would I insert something in between 10 and 42? This little thing here. We got 10, we got 42, we want it to go in between 10 and 42. I know you have to use the arrow operator, but give me the code. Okay. Give me the code that will insert something between second and 42. All nodes will have a unique memory address. Okay. So every time you call new, it finds a spot in RAM that's not used and puts it there. Now, the reason why I'm kind of drawing it kind of all over the place like this, some up here, some down here, is because, yeah, some of them could be up high in memory, some of them could be down low in memory. They're all in the heap. Well, there's absolutely no guarantee that they're next to each other, right? They could just be scattered all over the place. And because we have pointer tricks going on, then they're all kind of linked together. Okay. So imagine you've got a string and you're putting beads on a string or something. I don't know. And if you want to put a bead in the middle, you can cut the string open, put the new bead on, and then tie the string back together or something. Right? Whereas with a vector, the only way of making room is to push all of the elements one at a time to the right, and then put the thing in the linked list. You can just come in there, put the beat in, then string it up. Okay. So tip 10 says second points to next equals new node, 16 second points to next. Yes, that is correct. So if we do that, that will add a new node between 10 and 42. Okay, second is pointing at 10. So seconds next is the new guy. The new guy. Okay, seconds next is the new guy. And then the new guy's next is the artist formerly known as second points to next. So the previous guy that this guy's pointing to was 42. So his pointer is pointing at 42. Seconds next is pointing at 16. Everything works. And this is something you're going to see a lot of when working with linked lists, is a lot of the code is actually really short. New students will oftentimes write code that's like 10 pages long or something. And a lot of times you only have to write like 1 line of code or 3 lines of code or something like that. So let me show you guys how to print this, okay? So let's make a function called void print linked list, and it's going to take in a node pointer named putter, the Arthur Dwyer pronunciation. It's a putter, and we're going to print the linked list. And remember, every node in a linked list is a linked list that contains one data element and a pointer to another linked list. Okay, so we're going to pass in first. And so, yeah, it could be in Tron, you'd probably see a linked list as like a train station. I don't know. Okay, so the first thing we always do when working with pointers is check to see if they're null. Okay, and if it's null, what should we print if we say, hey, print a linked list? What if we said, hey, print a linked list, and we told it to print null? What should that print to the screen? If we say print an empty list, what should it print? Neuromancer, fantastic book. Also highly recommend Snow Crash. If you're a computer science major, I almost think that Neuromancer and Snow Crash are like mandatory reading. It should print 0. I would say it shouldn't print anything. So if you give me an empty list, so if the pointer passed in is a null pointer, just return, I would say. Print nothing. Oh, you're reading Snow Crash right now? Fantastic, fantastic. So there is a faster way of typing this, though. So this is why I left this number here as 0. What is 0? Is 0 true or is 0 false when it comes to computer science? Is 0 true or 0 false? 0 is false. So if I write this, it's exactly the same code. If putter is null pointer, return without printing anything. You guys understand? Because 0 is false, so not logical not, but false is true. So if pointer is false, return. Done. This is standard like C++ terminology. You will see this all over the place. Sometimes people will write if pointer double equals null pointer or whatever. This is probably more common. Okay. And so you could write this as null pointer here. Bjarne would approve. This is the standard C++ way of doing it. Simply because using a 0, everybody understands what it means. Everybody understands that means a null pointer. Null pointer is just a pointer to address 0. Everybody understands it. But it's an integer. And so if you did something by accident and like added numbers to it, that would be bad. So it is more correct to use null pointer there. But I use 0 for a second just so that you can understand why this works. Okay. And in fact, if you see out null pointer, it prints 0. Like it's literally just 0. But the benefit of using null pointer here is that if you try treating it like an integer, the plus operator will be like, it doesn't work. You cannot add anything to null pointer. It disallows all, it's not an integer, okay? Even though it is really just 0 under the hood. If you ever try adding something, if you try bit shifting it, it does not work. Null pointer will reject any attempts to treat it like an integer. Whereas when you use 0, it will very happily add 0 and 100 together. If you use null, which is the C version of null pointer, null is just a 0 also, and so you get these weird error messages and things like that. So the proper way of doing this is null pointer, but just understand that under the hood, it's 0. Really, it's just 0. Okay, you guys understand? This is the blessed way of doing it. So both of these are very commonly found in C. And null literally is just the number 0. It's just hashtag defined null to be 0. It just literally just turns into 0. This is the C++ way. Okay. So this is the good habit you should get into. Okay, but I wanted to put a 0 there just so that you understand why that works. Okay. So blessed be. Okay. So let's print the linked list. So if you hand me a linked list, you send me a pointer to first. I'm going to print the value here, 5. So do you guys remember how to get the X out of pointer? I've got a pointer at something. Do I use .x or do I use arrow x when you got a pointer? You have a pointer variable. Do you use dot or do you use arrow to get the X out of it? Yes, it is green arrow. Okay. So we are going to see out pointer points to X. Okay. And then watch this. We're going to do a recursive call. So we are going to say print linked list, passing in pointer points to next. So what we're going to do here, if I can type, is we're going to print 5, right? And then we're going to recursively call on the next, which is going to print 10, and then recursively call on its next. It's going to print 16, recursively call on its next, and print 42, recursively call on its next, and print 15, recursively call on its next. Its next is null. Null is false. We return. We're done. Okay. So, you guys understand? If we recursion, yes. All right. So let's do this. So first node, okay. So first is equal to new node 42. Okay, so take a moment. I will take a long drink of coffee. See if you can figure out what's going on here and what this is going to print to the screen. Okay. So we start off with a linked list that just has the number 5. So when we start off, first is just this. We don't have a second anymore. We don't have a third anymore. Its next is set to null. And then we're going to be doing some inserts on this list. You guys got to think about, is it coming in front? Is it coming behind? What's it going to print when we print the line? So I'm going to pause the recording now. Take 10 seconds or so to think about it. I'll drink some coffee, then I'll unpause. Okay, so let's compile and find out. 690, 420, 42, and 5. So what happens here is that when we print first contains a value of 690, right? We just nude something and we have 690 and it points at the old first. And the old first contains a value of 420 and points at the old first, which was containing 42, which points at the old first, which contains The value of 5, what's its next? Null. So it prints out 690, 420, 42, 5 backwards. Okay. So I could draw this out if you want. I'll just do the first one. So when we do this line of code here, remember the new takes place prior to the assignment. So it's not actually, it looks weird. It's like you're assigning first to itself. But just think of the new taking place first. And so it's making a new node whose value is 42 and whose next is pointing at first. So it does this. And then after the new takes place, then it assigns first to be that new memory address. So this thing here is now pointing here. And then when we do the next line of code here, you do the new first, right? And so it does a new containing the value of 420, and his next is the value pointed to by first, which is this guy. And then after all that's over, then we do the assignment of that new returns a new memory address, and first is now set to be that. And so that is what we're doing here. And so when we print out the list, it goes backwards, 420, 42, 5. Okay, that makes sense to you guys? Now, there is a different way of printing, and that is iteratively. So there's always, with these kinds of things, there's usually always a recursive solution and an iterative solution. An iterative solution is like a for loop. A recursive solution takes place because every linked list contains a linked list, right? Anytime you have a data structure like that, binary trees are going to be another one. Anytime every data structure that is a linked list has a linked list within it, there's usually a very short and beautiful recursive solution that works like that, where you do one work and then you recursively call on the child, and then it'll end up traversing the entire thing, and hopefully you don't Stack Overflow. So, because this code will actually Stack Overflow if your linked list is too big. You're going to run out of stack space maybe, and segfault. So a lot of times we prefer iterative solutions, even though the recursive solution is oftentimes option 1, recursion. Option 2, iterative solution. And that is using a for loop. And so this is a standard pointer traversal for loop. Learn this pattern. Okay. This pattern is the same pattern that you'll see a lot of with iterators, because iterators and pointers are more or less the same thing. And so an iterator begins at the beginning of a data structure and goes to the end of it. You're going to see a very similar for loop when you work with iterators. So for node pointer temp equals putter, using Arthur Dwyer's pronunciation there. As long as temp is not equal to null pointer, temp is equal to temp points to next. And so this is going to begin at the beginning of the list. If the pointer ever becomes null, it breaks. And so that even covers this situation, right? Where like if you pass a null pointer, it'll immediately check to see if it's null pointer. If it is, it just doesn't do anything. So cool. And then after we do our stuff, and what we're going to do here is we're just going to see out temp points to x. So we're going to print out the value, and then we move on to the next element. So this iterative solution here starts with temp equal to first. So it's going to be pointing there. Is this pointer null? What do you guys think? And if I wanted to, I can actually just do that. That's actually perfectly valid as well. Is temp currently null? What do you guys think? So we're going to run through this for loop. So the first time through the for loop, we passed in first here as our pointer, right? And here, printing at first. So putter is equal to first. So temp equals pointer. Is it null? We have to check to see if it's null before we do anything. Is it null? No. So what do? We print out the value held by this pointer, temp, which is 420. So it prints out 420, and then it says temp equals temp points to next. So temp equals temp points to next. So it is now pointing at whatever temp's next is, which is this guy. It then checks to see, is it null? Is it null? No. So it prints out the value of 42, and then temp equals temp points to next. And so temp is now pointing at you. And it checks to see if this is null. It's not null. Its next is null, but it's not null. And so it prints out the value of 5. And then it says temp equals temp points to next. And so temp is now equal to null. And that breaks the loop. Remember, because 0 is false. And so it stops the loop, and we're done. So this is a standard for loop for traversing a linked list. You will see this everywhere. Okay. It's very similar to the iterator pattern where you say, iterator equals vector to begin, as long as the iterator is not equal to vector end, iterator plus plus, or something like that. So if you write the code like this, you'll see it is exactly the same thing as what we had before, except we're doing a for loop instead of using recursion. And I personally would prefer the for loop way because I don't like my code segfaulting. So is it a big risk? Probably not. You would have to have a really, really big linked list before it segfaults. But at the same time, I don't like having code that segfaults. It's kind of a big deal for me. Like I like having my code not crash. So there's also no guarantee it will segfault because the optimizer might eliminate the stack frame for us. Maybe I wouldn't risk it. So I personally would choose option number 2. That said, a lot of students like the beauty of a recursive call. And so probably is not going to matter in this class. So we're going to do a little bit of lab time now. For lab time, I'm going to have you guys write a function named +5. Or was it first 5 in California now? We'll do +5. Okay. Node pointer. And what I want you guys to do for lab time, is write a function that increases the values in the linked list by 5. All the values. It increases all the values. So you have to iterate across the entire linked list and add 5 to all of them. So if we come down here and we do a +5 and a +5, then when we print it, it'll print out 700, 430, 52, 15. Okay. Your code for +5 is going to be very similar to this. Okay. I'm not gonna give you the answer though. I'm gonna give you guys some lab time. So I'm gonna push this out. Copy main.cc into public linkedlist.cc. Those are L's, not ones, by the way. And so if you guys want to copy this, copy /public ll.cc to your current directory, and I will put this up on Discord. Like that. And so hit that command, and I'm going to give you guys 10 minutes to write it. And you might discover another bug that we have in our code, but I'm not going to tell you. When you guys discover that bug during lab time, post it on the chat channel, and we'll see if you can fix that bug that I've deliberately left in there. Have I deliberate? Yeah, let's say it's deliberate. Why not? There is definitely 100% a deliberate bug left in there. See if you can fix it as well. Okay, lab time, 10 minutes only. Then you're going to post your screenshots of your +5 function, and then we'll come back and talk about it. Okay, here we go. All right, so what we want to do is, in general, it's a good idea to make a constructor like this. A constructor is in general kind of a good idea to have. C++ will sometimes stop making a default constructor for you. And so having a default constructor will especially when you do it like this is going to make a default constructor with no parameters. It'll make a 1-parameter constructor. It'll make a 2-parameter constructor. You just need to have one constructor, each one with a default in here like this. And then that's sort of like a universal constructor that just will work for all the 0 parameter, 1 parameter, 2 parameter, however many parameters you have if you do it this way. It's a good idea. And when your classes get complicated, C++ will tend to demand it. And then you can initialize your code with parentheses or with curly braces, and everything just kind of works. Okay, so the +5 function here, Messick, do you understand what's going on here? The +5, we got here code that begins at the beginning of the linked list, and until we hit the end, we increment each value in the list by 5, and then we go to the next one. Okay. So, not the delete. Okay. So, deleting this is going to be annoying. And the reason why it's annoying is because we've got only a pointer to the first one. We don't have pointers to the other ones. And so we could do something really, really tragically stupid like this. We could say delete first points to next, points to next, points to next. First is 690, next is 420, next is 420. Yeah. Like, we could do this. By the way, right, like, my code isn't showing the, my code is not showing the memory leak that you guys are seeing because my alias is set up differently. So if I come in here and say -f sanitize equals address, like that, you'll see now I'm getting memory leaks. So I'm leaking 3 objects because I'm deleting the 4th one, right? Right here. So if I really wanted to be obnoxious and stupid, I could literally do this like this and feel really bad about myself. And resolve the memory leak this way. No problem. But you should be looking at this and be like, there should be a better way of handling this deallocation than this. Yeah, you should probably use a for loop, okay? You don't want to write this by hand. This is stupid. This is really bad code. And you might be like, well, what if we deleted the first one first? Well, great question. What if we did it like this? What if we deleted the first one first and then firsts next? And what if we did it like this? Do you guys see any problems with this? Nope, this seems fine to you? If we delete first, can we access the next value after we've deleted it? You should feel a little guilty about that, right? Like, nope, like, don't do it. Is this going to be a null reference, dereference, cordon, segfault? What do you guys think? Is this going to be a null pointer dereference? What do you guys think? Yes? So you think that when you delete a pointer, that C++ will set that pointer to be 0? It doesn't. It actually leaves that pointer alone. So when you delete something, it actually doesn't change the variable at all. It deallocates the memory pointed at it. So if you do this code here, I'll show you what it'll do over on OneNote. So we got first pointing at 420. If you say delete 420, what it does is it comes through here and it deallocates that memory. First is still pointing at that memory. And so if you say first points to next, like first points to next here, it'll probably work. Maybe. It's not, there's no guarantee. You're in undefined behavior territory now. But you could say delete first points to next, and maybe it'll work. And then maybe you could delete first points to next, and it might work. It might work even. And this is extremely dangerous. Okay, this is one of the reasons why I have address sanitizer turned on for you guys and not for me, because I don't make mistakes. Sorry, I'm not recovered from my cold enough. Sorry, I'm getting lightheaded. Sorry. Yeah, everyone makes mistakes. That's why address sanitizer is so amazing. So if I run this code without address sanitizer, let's just delete this out here. If I run this code without address sanitizer, it might work. Double free? Yeah, okay. Sorry. Didn't work. It might have. Who knows? But with address sanitizer turned on, it will detect a use after free, which means you're using a pointer after, right there. Keep use after free. In other words, once you've deallocated a pointer, you should not dereference it. even though it might work. It might. This is not set to 0. It is not a null pointer dereference, but you should not ever use a pointer after you've deleted it. Okay? So just simply, I don't make mistakes. You heard it all here first. Yes. Anytime I make a mistake, it's simply an educational moment for you guys so you can learn what not to do. Okay. We'll go with that. All right. So what is the better way of doing this? So we should have like a node pointer temp equals first. As long as temp is not null, node pointer next equals temp points to next. Delete temp, and then temp equals next. Okay. So this is what you have to do if you want to actually delete it properly. And it's kind of annoying, right? It's kind of annoying. So what you do is you make a temporary pointer. Actually, I guess you could just use first because first isn't going to be meaningful after this point. But okay, so I've got a temporary pointer. The temporary pointer is pointing to first. And then I make a next pointer that is pointing at temp's next. I then delete temp, boom, boom, and I set temp equal to next. So temp is now pointing here. And then I set next to be this guy. I delete temp, and then temp equals next. Next equals the next guy, which is null. I delete temp, and then I set temp equals the next. So temp is now pointing at null. And then the loop ends. So you have to use a temporary copy is basically what it's doing. So you have to make a copy of next so that after you delete it, you can get the next. It's kind of annoying. So while pointer, null equals pointer, pointer equals pointer points to next, delete old. Yeah, so BD's code is basically the same thing, right? Yeah, that's cool. Yep, same code. You have to make it temporary, right? You have to preserve you have to make a copy so that you can still have the next after you've deleted it. Okay. When does temp break? When it is null. So remember, null is 0, 0 is false, while false ends the loop. Okay. So this is very standard C++ code. I could say while temp is not equal to null pointer. That's equivalent. I just don't like typing extra stuff. In the C++ world, everybody understands what this means. Okay. Everybody knows this is saying while temp is not null, right? Everybody knows null is 0, 0 is false. Once temp becomes null, temp becomes false, and it breaks. Okay. +5. Yeah, you should not put the delete pointer into your +5. Yeah, so typed in your code. You've combined together your +5, your cout, and your delete all at the same time. Yeah, don't do that. You want to have a separate function for print, a separate function for increasing by 5, so you can do it multiple times, right? And then here, I'll put up on the screen here. Yeah, so you don't want to do all these together. And also, this is only deleting the first element in the list. This is not deleting the whole list. It's just deleting the first element in the list. So, yeah. When I took 41, you thought linked lists were the best data structure because they're easy to implement. I guess. I mean, it's not too much code, but yeah, linked lists don't have much value except when you are doing a lot of inserts and deletes from the middle. That's when they're good. And that is not very common. Like, there's not many. Like, there are times where I've used a list, certainly, but it's about 3% of the time. Something like that. Between vectors and hash tables, that's like 90% of my data structures. And then linked lists are like a couple percent, maybe. Okay. So, if you ever forget how to generate a destructor for a linked list, there's always ChatGPT. And so the trouble with this is that a lot of the ChatGPT stuff is actually wrong. Like, I was asking some questions, like, because I'm trying to figure out like how accurate it is, right? And you can do things like this, like write a rap song in the style of Eminem. Yo, it's your boy, the one and only, the king of the rap game, so listen closely. I got bars for days and rhymes for miles. Yeah. Justin Bieber is really cool with his music. He makes us all drool. But I was asking questions of it, like what's the capital of Florida? It's like Tallahassee. Cool. Why is it the capital? And it gives a wrong answer, right? The answer is wrong. So the capital of Florida used to switch between Pensacola and St. Augustine every other year, and people got tired of it moving, so they just picked a town in between. That's why it's the capital. And then for the Battle of Sitka, I asked about the battles of Sitka between battles of 1802 and the 1804 ones, and it's basically all wrong. It's all just wrong. So, I mean, yeah, okay, fine. There were two separate military conflicts that took place between the Klingits and Russian colonial forces in what is now Alaska. The Klingit were unsuccessful. That's wrong. The Klingit won the battle of 1802. They basically attacked a fort. The Russians were building a fort on Klingit land without permission. Klingit came in there, killed them. Only a couple of people survived. They fled. 1804 was a retaliatory strike by the Russians against the Klingits for the Battle of 1802. So it's completely wrong. Like, so you guys, I don't use ChatGPT to plagiarize A. But if you ever like want to look up like how do I do something, please explain link to this using memes. Not good. Me trying to explain link to this. A picture of a cat holding string in its mouth with a caption that reads, "Me trying to explain link to this to my friends. Cat, here, I have the string. Pull string to reveal a series of connected knots, each leading to another string. Each knot represents a node linked to this, and the strings connecting the knots or the pointers are linked." It is not funny. It is not good. Okay, but I did have it generate a destructor for a linked list, and it's actually correct. So this is actually ChatGPT is really bad at humor and memes and things like that. So I had it generate a destructor for a linked list, and if you look at it, it's actually the code that I just typed up a second ago. Make a pointer to the beginning while the current while it's not null. Next, make a copy of the next pointer, delete the current, and then set current equals to next. So that's literally the correct code, and I told it, all right, write it again using comments, and so it actually explains what each line of code does. So you guys can use ChatGPT as maybe a tutor. I would not copy and paste code off of it. For one thing, it's plagiarism. For another thing, it could be wrong a lot of times. So it can answer certain simple questions accurately. Yeah, I don't know. Like the battles of Sitka is just wrong. Like it just has the wrong, like it just has completely wrong information about the Battle of 1802. Like it thinks it was a Russian like victory and it wasn't. So okay. So yeah, you can see the code that it made there though was pretty similar to this code. So that's the thing about ChatGPT is that you still have to have somebody with the experience to know if the stuff coming out of it is actually correct or not. So all right. So that was phase 1 of the homework assignment. Now we're going to do phase 1 of today's lecture. Now we're going to do phase 2, which is doing this again, but proper like. So we're going to actually do this. Delete, Shift G, boom. We are actually going to make a class. So we are going to go from like real basic with main, doing the pointers and stuff like that. We're going to go from that into a full-on ADT. Okay? So we're going to make a linked list class. And inside of this class, we're going to have a pointer called head. And then we're going to have a public section. And as always, we're going to have a linked list constructor that does nothing because this is already doing the only thing we need. And we're going to have our standard functions of insert a new value, and we'll write this later. And we're going to have a remove function, and we're going to have a search function, and we're going to stub it out by just returning false. And we're going to say you're going to do this part, and you're going to do this part. And then we can have a insert, remove, search, and print, maybe. And now I say, man, I should not have deleted that code because it's Okay, so for head pointer equals head, as long as pointer is not null, pointer equals pointer points to next. Not head pointer, sorry. Don't type and talk at the same time. Node pointer, cout, pointer points to x. Okay, there we go. So now in main, we're going to do things all proper like. Okay? We're going to do things properly. We're actually going to make a linked list class named list. And we can say things with dot instead of arrow. That's cool, right? Arrows are scary. Pointers are scary. All of the pointer stuff are actually going to be in the linked list class. Okay? And so list.insert. So we're going to insert 5 and, I don't know, 10 and 50 and 5, 12. And then we're going to print it. Stop print. Okay. So now this is better because in main before, main was like messing with the pointers and main had to have a for loop to delete all the things. And that's kind of garbage, right? Because the people in main aren't going to know to delete things and how to delete things. They have to look at your implementation to figure it out. It's much better to encapsulate everything like this into a list. And so you have an interface. This is the only thing that the people in main need to know about, is that you've got an insert function, you got a delete function, you got a search function, and a print function. That's all they need to know about. They have to know nothing about how you've actually implemented your linked list. It's nice. Okay. Now you might be asking, what the hell is going on here? Thank you. What the hell is going on here? You have a class inside of another class. Like, what? You can do that? Mm-hmm. Yep. This class is only accessible because it's a private, it's in the private section, right? So only the linked list class knows about the node class, okay? So now nobody needs to know that you've got nodes, right? Like in Pitch Perfect. Is that like recursion? It's not exactly. It's more like I heard you like classes, so I put a class inside of your class so you can class while you class kind of thing. So what's going on here is we have a class called node. And if you want to think about this conceptually, I can put it up here. Does that make you feel better? It's the same. It's going to be the same for our class. But see, now main can see the node class now. And it doesn't need to. Main has absolutely no reason to know anything about the node class, right? If you want, conceptually, you could write the code like this. It'd be just fine. Your code is just fine like this. But you can tuck a class inside of another class. And now this class is only accessible to things within the linked list class. Does that make sense to you guys? So all of these references to nodes and things like that, like if I was down in main now, and I said something like, make me a new node pointer equals new node, 5 and null pointer, doesn't work, right? Never heard of this person in my life, right? Because it's in the private section, okay? So, pip my class, exactly. And so because main doesn't need to know about the node class, because it's one of those implementation details that doesn't matter, right? Am I using pointers? Am I using vectors under the hood? It does not need to know anything about how I've actually implemented it. All it needs to know is it can insert a value and search for a value and so on and so forth, okay? So our constructor is pretty simple there. Do we need a destructor? And what about a copy constructor and like a move assignment operator and a assignment operator and all that kind of stuff? Are we going to need it? Does our class know anything? Not yet, but will it? What do you guys think? Honestly, quite incredible. Yeah, I think we actually probably should have a linked list destructor. And list. Yeah, don't type and talk at the same time because it's dangerous. Linked list destructor. And it's basically the same code that we had before, which I've unfortunately deleted. So let's see here, node pointer temp equals head. Actually, we'd probably destroy head. That would work too. Okay, so while head node pointer temp equals head points to next, delete head temp equals temp points. Head equals temp. There. And that is a destructor. Temp. It is going to make a copy of heads next. So it makes a copy of this pointer here, then deletes that guy, sets head to be that, moves next to there, deletes this guy, moves head to there, sets next to null, deletes that guy, sets head to null, then the loop breaks. Okay. Or you could have copied that off of ChatGPT. It's the same code. Okay. Do not make a recursive destructor. Really don't. It's a bad idea. Segfaulting when you go out of scope is a terrible thing to have happen. All right. So we got a print function, we got search, we got remove. Let's do an insert. So let's do an insert at the beginning. Insert at the beginning of the list. So if we've got 5, 10, 15, 20. Okay. So the first time through, we're inserting 5 and head is null, right? The first time that we insert something, head is null. Okay. So we could do something like this, like if head is null, or something like that. But we don't need to. Watch this. I'm going to give you guys a bit of magic here. So we say head is equal to new node holding in value and head. Boom. One line of code. This might look familiar from what we did earlier. So the first time we call insert, we're passing in 5 for the value, so this value is 5. Head is null, right? Default initializes to null. So when we call new, remember the new takes place before the assignment. So just focus on the new for now. It's going to create a new node whose value is 5 and whose next, right, is null. So the first time we call insert, the linked list is going to look like this. Yep. Head is pointing at this. Its value is 5. Its next is null. All right. One line insert. Okay. Next time we do an insert, we insert 10. Okay, so coming up here, the value is 10. Remember, the new takes place before the assignment. So we're going to make a new node whose value is 10 and whose next is equal to the current head. So we're going to make a new person in here who is the value of 10 and whose next pointer is pointing at the current head. And then head will point at it here. This is only, we're doing an insert at the beginning. Okay. If you want to insert at the end, that's going to be an order in operation because we don't have a tail pointer, right? So if you wanted to insert at the end, you would have to like do a for loop and go to the very end of the list and then attach it at the end. So for today's lab section, we're just inserting at the beginning. Okay. So let's compile this code. And you can see here, it is printing out the numbers backwards. You guys see why it's printing out backwards? 5, 10, 50. This guy hooks up to here. And then we insert 512. This guy points here. Head points at here. So when we print it out, it prints out 5, 12, 50, 10, 5. All right, we're inserting in the beginning. We're pre-pending. Okay, so what you're going to do for your lab time, and I'm going to give you guys 15 minutes to work on this, and then we'll talk about Bridges Shakespeare for the last 10 minutes of class or so, is I want you to work on search, and you should be able to use the code for print to make code for search that will return true if the value is in the linked list, and return false otherwise. And then see if you can figure out remove. And if not, we will talk about it probably on Monday then. Okay. So lab time begins now. All right, we're back. I'll get copyrighted striked. Okay. So we are going to have you guys post the answers. See what you guys got. I'll give you guys mine while you guys post yours. So like I said, the code for search is going to be pretty close to the code for print. This is a standard linked list traversal algorithm like that. And what we want to do is say if the pointer points to x double equals a value that we're searching for, it will return true. If we get through the whole thing, some people will do this, right? They'll say else return false. This is bad, because then you're going to search the first one and then immediately return. So what you need to do is wait until you get through the entire linked list. If you find the value in none of them, then we return false. Okay. So let's see what we got here. So Hockman, your code is not correct because it needs to return true or false. Your code is currently printing a value. Printing a value is not the same thing as returning a value. So that's a common mistake that students make, though, where they see out something when they should be returning from a function. That one's correct. Okay. Stokes looks good. Alessandra didn't finish it. Tall looks good. Zofka looks good. Okay, so yeah, looks like nobody got to remove. That's fine. We'll put this off till Monday because you're not going to need it for the homework. What I want you guys working on, because the homework's due on Wednesday, I want you guys working on the homework over the weekend. So let's go to the homework site, which is called Bridges Shakespeare. Now for Bridges Shakespeare, there's kind of two halves to it. The first half is kind of what we worked on Wednesday. It's histogramming. You're going to open a file. You're going to count how many times that word appears in the file. And then you're going to visualize it in the second half. You're going to visualize it using a linked list. So you're going to have a linked list with all of the most common words in it. The top third will be marked, will be colored red, the middle third yellow, the bottom third green. If you want to see what this will look like, finish this already. Run it, desktop text. And so this has, hello, my name is Inigo Montoya, prepare, something like that. So prepare appears 3 times, and then it puts up a list like this. Oh, I'm not streaming. Okay. Always happens, huh? All right, there we go. All right. ChatGPT make me Kearney's code. Yeah. Well, anyhow, yeah, Zofka's code's correct. All right. So here's what it looks like when you finish it, right? So prepare is at 3, hello's at 1, and you go Montoya. If there's a tie, it doesn't really matter what order they come in. And so this is a linked list, okay? For something that is bigger, I have Titus Andronicus on here. So I have all of the works of Shakespeare on here. And so you can see when you histogram it, these are the top 30 words in the histogram. And when you visualize it, it's going to give you a URL. And there we go. You can see the top 10 are all in red. And there's a little arrow pointing at the next one, so you can see it's a linked list. Now, Bridges is made by the University of North Carolina at Charlotte. And it was really designed for this class. It was designed for CSI 41 as a way of being able to visualize common data structures so that students can see what's going on. And so if you screw up your pointers and stuff like that, you'll actually see it screwed up on the visualization. So for this assignment, the actual shape of the linked list doesn't matter because it's a line, and so you can, kind of move these things around however you want. It doesn't really matter. But the top 10 should be in red, the middle 10 in yellow, and the bottom 10 in green. Okay, and that is what you're going to be doing for this assignment. Okay. Let's take a look at the starter code here. The starter code, there is a place here where you need to enter your username and API key. Okay. And so if you go to the Bridges website, UNCC Bridges, there's a place where you can log in. And then when you click on your profile after you create an account, you can see your username and your API key. And so the API key is like your password. I've just revealed my password to everybody, except I can just click and make a new one. So the second I minimize the screen, I'm going to make a new API key, so you can't do anything as me. But I can just sit there and just make new API keys whenever I want. And so what I'm going to do is I'm going to copy W. Kearney and put that into where it says username. I will copy API key and put that in here, and then you're all set. Okay. So that is, and then I'll make a new API key. There we go. And it is now hidden from you guys. And so you can see that you can make little visualizations for different data structures and things like that in it. And they've got all sorts of different ones. This is a graph. Chess, and this is like a shortest paths kind of assignment. I think we did that in Porty last semester. Just Tahoe, navigating around through Tahoe. And, they have integrations with like OpenStreetMap, so this is actually Fresno, and it's actually navigating to the college and stuff like that. So Bridges has a lot of cool stuff in it. This one is a fairly simple implementation, okay? So, yeah, the API key's already been revoked, so sorry. So you're going to punch in your username here, your API key here, all right? And then the first half here is all histogramming. It basically tells you every single thing you need to do. There's a lot of hand-holding on this assignment. Then it's going to make a linked list from scratch. It's got a head pointer, which they call root. It's got a current pointer that's going to be used to iterate through it. It shows you how to set the color of a node to white. You need to change these to red, yellow, and green. I'm not going to tell you which word you need to change to make it red, or what word you have to type to make it red. I'll let you guys figure it out from the documentation. Okay. Then this builds the linked list. There are 2 lines of code you have to write to make the linked list work. One is setting the next of the current pointer to be the temp. So the new guy gets attached at the end using the set next function. And then you have to set the last. Current is like the last pointer, the tail pointer in the list. The last of us. So what you do is you've got the last pointer, which is called cur for whatever reason. We make a new node and set cur's next to be the new node, and then we move cur to point to the end. And then that's it. It's 2 lines of code. You should be able to do it based on the hints that I've given you here. And then the rest of the stuff is done for you as far as making the linked list and stuff goes. And then at the end of the code, it visualizes it. Okay. You need to type blue. That's exactly right. You have to write the word blue here. Okay, so that's your assignment. It's a slow introduction to linked lists where you only have to write a little bit of it. Most of it's done for you. Then your next assignment will be more in-depth in linked lists. And that's our class for today. Do you guys have any questions about linking lists together? The less than operator, this is actually a really important thing in C++. The less than operator allows you to sort things, okay? So anytime you have a vector of something and you want to sort it, like if you call sort on a bunch of words, it uses the less than operator, okay? And if you want it to sort from greatest to smallest, you can change the direction the greater than sign is in. Or you can use r begin and r end, which is probably the better way of doing it. Documentation for their linked list class is here if you want to read it. If you want to find out what exactly you must type to change it to from white to red. No spoilers. It's 3 letters long, though, the string you have to type inside of the double quotes. Okay. Yep. So I would work within the word class that I've given you here. And yeah, the main thing is understanding that operator lesson is actually really, really important. It's actually the most important operator because it is very common for us to want to sort things from less to greatest, least to greatest, and the less than operator lets it be done automatically. So you just can sort a vector of words now once you got your less than operator defined. Can I give another hint? Yeah, if you want to change the color to yellow, there's going to be 6 letters inside of the double quote instead of 5. That's all I can say there. No more hints. No more hints. Yellow is 6 letters, I think. Shoot. Did I say that out loud? Dang it. All right. Never mind. Okay. That's it. Class is over.